All right, folks, welcome to our first edition of Social Isolation Lecturing. I'm coming at you from my home office here. So, a couple things I wanted to mention before we get started today. First thing is we are supposed to have an exam this week. And so, what I'm going to do is I'm probably going to post that exam to Canvas on Friday, and I'm going to give you guys a week to do it and send it back to me digitally. Um, I'll post some more details on that when I know some more details on that, quite frankly. Okay, and then the other thing is I'm still kind of figuring out how we're doing these videos, and so that means that at least today and possibly in the future, couple of suboptimal audio situations so far, and you're probably gonna hear my kid and my dog in the background. We're just figuring out how this stuff works together here, folks. But yeah, I think other than those caveats, I think we're ready to jump into the lecture. Today we're going to talk about size exclusion chromatography as a mode of separation in liquid chromatography, and we are going to talk a little bit, not too much, but a little bit about chiral separations and how stationary phases in liquid chromatography are designed to achieve separation of chiral molecules. So let's jump into it. Okay, friends, let's review what we were talking about before we left for the break. We've been talking about modes of liquid chromatography. Okay, and we had gone through a couple of these so far. We had talked about adsorption chromatography. And this was the original classic chromatography experiment from Mikhail Sep'ns. This is on silica particles or alumina particles. And basically the take-home story here was that these surfaces are essentially too high energy. There are too many functional groups. There are too many intermolecular forces that allow molecules to bind to the surface, and so retention is essentially too strong. You'll remember back when we were talking about retention factors, and we said basically chromatography ends at a retention factor of 15. We went through some math on this, and we talked about how your resolution fails to get significantly better once your peak has a retention factor greater than 15. Your peak efficiency fails to get any better. And so we say we kind of lose all of the objectives of doing good chromatography at retention factor of 15. And so that's the problem here, is that our retention factors are all going to be really huge because these surfaces hold too tightly. We also talked about ion exchange. Yikes, there we go. Ion exchange chromatography. And this was a neat technology. The idea here was that we can have some actual formal charge interactions that interact at that cause binding at the stationary phase particle. So your analyte is a cation, the stationary phase has a negative formal charge, and so these things will coordinate together and you'll get really strong retentions. We kind of put this into two categories. We talked about strong versus weak ion exchangers, where the difference here was that these always have charge. The stationary phase is always charged, whereas these have this acid-base chemistry property, so we can turn that charge on and off on the stationary phase. And that allows us to tweak not just the strength of the mobile phase, but also the binding capacity of the stationary phase using pH as a mechanism for doing that. And the thing that we were talking about when we left, and we're just going to kind of start back over with this because it's been a while and the entire world has been imploding on us while we've been gone. So I forgive you if you've been a little distracted from it. The thing that we were talking about, we're going to start back over with again today, is size exclusion chromatography. Okay, so what does this look like? So size exclusion chromatography is, as the name suggests, a size-based separation. So size exclusion chromatography, we are going to abbreviate SEC, just like the Southeast Conference, I guess, if you're into that kind of thing. I'm a Florida State guy, so I'm into the ACC, but whatever. Size exclusion chromatography is a size-based separation. And what we see in these chromatograms is something that looks like this. I think this is the very last thing I drew on the board before we left and the world imploded. We see these peaks. Okay, and we said that basically the smaller stuff has a higher retention factor. And the larger stuff, larger particles, have a lower retention factor. And we said there's these two special peaks, right? I'm going to call this 1. I'm going to call this 2. So what are these? Well, peak number 1 is called the total exclusion peak. And what's happening in the total exclusion peak, these are all molecules or particles or materials that went through the column, all analytes that were too large to partition into the stationary phase. We'll take another look at partitioning in the stationary phase in just a second. We'll draw out the figure that we drew out last time. But real briefly here, we'll point out that this means that there's no size-based resolution, RS, above some critical size. Right? So everything that's too big, whether it's very, very, very much too big or whether it's just a little too big, everything that's too big is going to get clumped into that one peak. Okay, the second one here, 2. This is called the total inclusion peak. Total inclusion peak, forgive my hand there we go. And this is basically all analytes. Small enough to partition into all stationary phase pores. Hope you guys can see my handwriting here. I'm going to do a little bit better as this online semester goes on. Okay, so everything that's small enough to partition into all the stationary phase pores. So let's remind ourselves of the picture of what this partitioning process looks like. And this we drew on the board. This might already be in your notes because we drew this on the board before we left. But of course, we were all fearing Armageddon, so maybe we forgot to get it in our notes, or maybe we burned our notes to stay warm. I have no idea. Something crazy is going on out there, guys. But the concept is this. You have a stationary phase particle. We're going to draw just one of them. There's a stationary phase particle. And these things are not solid sphere. They're not usually solid spheres like I've drawn this. They're usually porous, right? So they have these pores. I'll draw them like crags going deep into the depths of this particle. And you can see that these pores have various different sizes, right? Some of them have big openings. Some of them have relatively smaller openings. There are these narrow constrictions that can be present in the middle there that prevent things from getting past. And so if we have a range of sizes of particle or analyte, there we go. And these things can diffuse in solution past this particle, while these small things are going to have no trouble diffusing all the way in here, right? But larger particles, like this one, for example, they may be able to get into part of the pore, but there's going to be some restriction at which their only option is to come back out. Again, all just by diffusion, all just by random walk motion in solution. And still, there's going to be other particles that are so large that they can barely. So I think, I don't know, just the way I've drawn this, that's probably large enough to spend a little bit of time like that, maybe, inside that particle. But this guy for sure, too big, can't get in at all, right? So this thing spends no time in the stationary phase particle, all of its time in the mobile phase particle. Sorry, in the mobile phase, right? Moving in the mobile phase past the stationary phase particles. And so this is this basis of separation where small things spend a lot more time in the stationary phase. When they're in the stationary phase, they are stationary. Surprise, surprise, spoiler alert. But when they're in the mobile phase, they are mobile. And so they are moving faster towards our detector. That means that these things move faster and come out first. They elute first. That's the same thing as saying they have a low retention factor, which is lowercase k, right? Whereas these things, on average, move slower because they spend more time stationary inside the particle. They elute later, exactly as we just described in the chromatogram. And as such, they have, where am I going to write this? Here we go. They have high values of lowercase k. And so the example that we talked about last time, the thing that gives rise to this concept of total inclusion and total exclusion peak is if I take another particle here, a really, really, really big one. It has basically, we're going to say that's a little bit bigger than that. I don't know if it really is. But it basically has the same access to inside this particle that that one did. And that gives it the same value of retention. They will both end up, despite being different sizes, in the total exclusion peak. And we can imagine even smaller particles here that also have full access to every depth of every pore. And so there will be no resolution here either. They will have the same K values and they will end up in the total inclusion peak. So let's think of a mathematical way to discuss, or at least a numeric, a quantitative way to discuss this concept of total inclusion, total exclusion, and resolution in size exclusion chromatography. And it starts with a concept we've used over and over again, but I'm going to remind you of it right now, which is, so our x-axis here is time, and we get peaks, right? Chromatographic peaks. And we are used to thinking about these in terms of their retention time, T sub r. Or if we really care about describing these things in a reproducible way that we can transfer to other labs that describe the extraction and not just the amount of time it took to come out in our lab, we can convert this to a retention factor. But there's another thing we can convert this to, and we've talked about this. If we know the time it takes for something to come out, and we know the volumetric flow rate, so just to be clear, volumetric flow rate implies something in units of volume per unit time. If we know this, and we know how long it takes to come out of here, we can talk about not its retention time, but its retention volume. We've talked about this being a really useful factor, useful way of describing retention in gas chromatography, especially, but it's also very useful here and really can be used in any mode or any method of chromatography. So this is our retention volume. And pretty much all the math that we've done that applies to TR applies to VR. We just need to put our brains into the kind of the volume way of thinking, right? So let's talk about, in terms of retention volume, what these total inclusion and total exclusion things mean. Okay, so first let's start with total exclusion. So if we're saying that a particle is too large to interact with the stationary phase, it is by definition an unretained species, right? And we had this terminology we used to use when we were talking in time about the void time, T0, which we said was always this first little blip of a peak that comes out, right? We'll call that T0. And we called this the void time, which is directly equal to the void time, which was also referred to as the time for an unretained, that's the key here, unretained species. Okay, we can convert that to volume, and we can call it V sub 0. So if our particles are too large to interact, if our analytes are too large to interact with the pores of our stationary phase particles, then we can assume that their retention volume, so the total exclusion peak, the retention volume for that, V sub r, is equal to our void volume. It is this unretained species. So cool. That's a fairly straightforward description. Our total inclusion peak is something else, right? We're saying that it samples the species in the total inclusion peak has sampled all of the intraparticle volume, all of the porosity of the stationary phase particle. And so in this case, what we can say is that its retention volume, V sub r, well, it certainly sampled the same amount of extra particle volume, the V sub 0, that it takes to get from the head of the column out to the detector, right? All of the extra particle space, but it's also sampled all of the intra-particle volume, which we'll call V sub I. Let's define this over here. V sub I is the intra-particle volume. We've called this before the total porosity of the column. Okay, so we are used to thinking of these things as extractions, right? And it's a little bit difficult for us to think about a partition coefficient here because what we're saying is that there's no enthalpic contribution to extraction, right? So it's difficult to think about it in terms of equilibrium constants. But basically, we can describe the partitioning coefficient in an experiment like this as being the retention volume of the species that we are trying to measure a partition coefficient for minus V sub 0. So this is essentially equivalent to our K factor, right? We can divide that by the intra-particle volume, V sub I. And if we kind of say these are the boundary conditions, right? The total exclusion and the total inclusion, what we end up seeing is that all of our separation happens in a space of this partition coefficient between 0 and 1. So it says between, got a little ahead of myself here, between 0 and 1. So in other words, total exclusion peak, K is equal to 0. And for our total, move this up here, see a little better, for our total inclusion peak, K is equal to 1, and all of our resolved space between these two, we have partition coefficients somewhere in that range from 0 to 1. Okay, so let's take a look at the space that we're resolving in here. So we'll call this y-axis. To be honest with you, we generally think of this as molecular weight, although any polymer chemists will tell us that molecular weight is not directly a stand-in for size. You can have something that's very heavy and very compact, and you can also have something that's very light, but also diffuse, right? Low density, and so it would have a very large particle size. So the real thing we care about here is size. It's very common to hear this reported as molecular weight, and that's because people are doing this, they're comparing their system that's very well defined, I don't know, some highly branched polymer or some very low degree of branching polymer they're using this technique on. And so they basically are telling you they're normalizing for the size factor. They consider this to be a molecular weight based separation. Okay, so we're going to plot that on the y-axis. We're going to plot retention volume on the x-axis. And what we said is there's some large molecular weight above which we're going to get no resolution. Everything's going to have the same retention volume. It's going to come out as the same peak, right? So it's all of this right here. All these molecular weights come out at the same retention volume. There's some low molecular weight, some low end of this scale where everything samples all of the stationary phase pores. And so they all come out together. They all have the same retention volume despite having different molecular weights. But the space between them, we hope to have a nice linear resolving range between them. And you can essentially select your column materials for essentially better resolving ranges in here. And what that would do is it would squeeze your total inclusion and total exclusion peaks closer together in retention volume, but it would also give you a steeper slope of this resolving range. And that means you'd be able to resolve two peaks that are more similar in molecular weight or size. You'd be able to resolve them a little bit better. But the take-home message here is for this original curve that we just drew, this is the range of retention volumes that correspond to k equals to 0 and k equals 1. Okay, so we get these linear resolving ranges, and they lie between k equals 0 and k equals 1. And they show some range of molecular weights for which we will get effective separation by size exclusion chromatography. But the question that, as an analytical chemist, you're going to need to answer is: I have two sized analytes. Am I going to be able to resolve them on a given column with a given method? And it's a hard question to answer outright, but there are basically two pieces of information that you can use as a rule of thumb to figure out whether or not this is going to work. And so the first thing I want to show you is this website from GE, Health Care Life Sciences. It's basically their product page and sort of introduction to size exclusion chromatography. It's actually a really nice page, and I'm going to try and link to this, if for nothing else than for the animation that they show right here of how size exclusion chromatography works. It's very, very neat, and I will try to make sure you have the link so you can take a look at that. It's basically just an animated version of the particle porosity thing that we drew out a couple minutes ago. But this is a kind of a product listing of their various stationary phase materials. They call it Superdex or Superose or Cefacryl. And what it's showing is basically the molecular weight ranges. So you can think of these as AMU or Dalton, ranging from 100 AMU all the way up to, what is that, 100 million AMU. They're showing the different products' ability to basically have that linear range between what this would be total inclusion to total exclusion for each one of these lines that lines up with one of their products. So that's the first piece of information you need, just to understand what is the resolving range. Actually, if you go to the Wikipedia article, this is the Wikipedia article on size exclusion chromatography. There's actually a table in here that I think is pretty nice, that looks at some really classics of these Sep'ns and Sep'ros materials. What these are cross-linked agarose. They're the classic material that size exclusion chromatography is based on. Basically, if you've ever done something like a DNA gel or a polyacrylamide gel, if you've ever done any biochemistry kind of work, it's basically those materials, except rather than just a matrix, like a porous matrix, they're actually chemically cross-linked. So it's the same underlying polymer substrate with chains cross-linked to give them nice high stability inside one of these packed chromatography columns. Anyways, the point is they these Sep'ns and Sep'ros materials, and if we go back here, you'll notice these have names like Sep'acryl, right? So these are very similar materials. They come in these different flavors or these different model types, and they correspond to different resolving ranges, right? So this is another nice useful table right here, especially since this is not linked specifically to the GE brand of offerings, but kind of the classic Sep'ns, Sep'ros type materials. Okay, so first piece of information you need if you're going to answer this question, can I resolve my two peaks, is what is the resolving range? And this is the linear range on that chart that we just drew a minute ago. The second piece of information you're going to need is what is the peak capacity? We've talked about peak capacity before. This is essentially the number of baseline resolved peaks that you could possibly include in a chromatogram. And it turns out peak capacity for size exclusion chromatography isn't great. So we've talked about kind of peak capacity approaching on the order of 100 or dozens maybe for classic HPLC, reverse phase HPLC, which we're going to talk about soon. Here, this is a paper from 1992 in Journal Chromatography A. This is like the top journal of separation science, basically. Looking at exactly that, peak capacity of common columns in size exclusion. And basically, here's a rule of thumb number 13. You're going to get basically 13 baseline resolved peaks. So if you take, remember these are these nice linear resolving ranges based on that graph we drew a few minutes ago. So if you take this range, for example, for Sep'ns G10, and you break that into 13 equal parts, will your two analytes that you're interested in land in two different regions of those parts, right? And if they do, you can have some confidence that your species are going to resolve by size exclusion if you're using this material and you're following best practices of the methods designed for this material. So take-home message, we're not talking about super high resolution here. We're talking about pretty poor peak capacities divided across what can be, let's take a look here, what can be some really, really broad molecular weight ranges. So we're not talking about resolving, 100 kilodaltons from 100.1 kilodaltons, right? We're not talking about a 100 Dalton resolution at the 100 kilodalton level. These are generally methods for separating very large protein complexes or very large polymer products from very small protein complexes or very small polymer products.
Okay, so just a few more practical considerations that we're going to need to be able to dive into the literature on size exclusion chromatography. The first is that, okay, so we call it size exclusion chromatography, SEC. But actually there are other really common names for this. So it's often called gel permeation chromatography. That's GPC. or gel filtration chromatography, GFC. The thing to know is that these are all the same thing. It's the same separation mechanism. Um, the concept gel here comes from those materials we were just talking about, Sepharos, which is cross-linked agarose, and other materials that originate as hydrogel materials from mostly from the biochemistry community and protein separations. And so we basically look at a mechanism where particles are made of gel and how deeply do these analytes permeate into those gel particles. It's the exact same thing. So I mentioned biology as kind of the origin of some of these materials. It's also one of the key application areas for this, right? Uh, so applications of SEC. First of all, in biology, one of the things people like here is to look at what we call quaternary structure or fourth degree structure, quaternary structure, which implies, just not to give a huge biochemistry lecture here, but the primary structure is essentially the sequence of amino acids. Secondary structure is kind of a two-dimensional folding of that sequence. The tertiary, the third degree structure, is sort of the 3D structure of this thing. So quaternary structure implies the macro structure that proteins make with each other. So when multiple proteins come together to form complexes, and you can imagine two large proteins coming together to form a complex, it's going to be a very large structure. And so it can be very useful to have size-based separations to study and isolate these things. So that is one of the big application areas, and other just kind of general protein purification. Um, and then it is highly used in polymer synthesis or characterization, polymer characterization, um, as both size-based purification, but also as a means for studying polydispersity, which is something that you can get from dynamic light scattering. I know a lot of the groups in our department use DLS for this purpose, but you should know that size exclusion chromatography and studying the shapes of the peaks essentially as they come out of this resolving range gives us some information about the polydispersity. If you are not a polymer scientist and you don't understand polydispersity, that's okay. We're not going to learn it here. But understand that this is another major application for size exclusion chromatography. I guess the last thing I'll tell you is that SEC is used both as a prep technique, and so that means that in the kind of the large volume, things like flash chromatography, which we've talked about previously in the semester, formats, you can get size exclusion or gel permeation or gel filtration columns, and also as an analysis tool. And we can actually see some evidence of this in these applications that we just looked at, right? If you're looking to do a size-based purification, this is likely a prep application. If you're looking to purify proteins, you're likely doing some prep work. If you're looking to study the polydispersity of your synthesized, polymer mixture, or to understand factors of binding, right, of quaternary structure in protein complexes, that's likely an analysis-based application. So I think this is going to close out what we're going to say about size exclusion chromatography, and the next thing we are going to move on to is chiral separations. Okay, so we are talking about chiral separations in liquid chromatography. And in general, there are essentially two approaches, two ways to separating molecules based on their chirality. The first approach is to use a stationary phase that is functionalized with chiral functionality, basically. So we'll call this a chiral stationary phase. There are kind of two, sort of three ways to do this. So let's take a quick look at what these ways are. The first, we'll call these, some people call these brush type phases, or a more common, maybe, or a more descriptive is the Perkle type phase. So the concept here, and we're going to switch to a screen capture here in just a second. The concept behind these Perkle phases is that you have a stationary phase that is dangling off a molecule with a lot of functionality that's going to give intermolecular forces. So you see a lot of pi stacking type functionality, so conjugated rings. You see a lot of hydrogen bonding and dipole type functionality, but the idea is all of this functionality is centered around some kind of chiral center, so that if you have two species that are essentially identical, but they are two, right-handed versus left-handed, R versus S, one will more preferentially interact based on the chiral orientation of these functional groups. So let's switch over to a screen capture. I'll show you a picture of what these things look like.
Okay, so here's that kind of structural motif of the chiral stationary phases that we were talking about. So full disclosure, how this is just something posted on ResearchGate. I actually don't know what paper this is or where it comes from. I just got here by doing a Google image search for Perkle type chiral stationary phase or something like that. And it landed on basically this image, which is what I wanted to show you. Before we go through this, let's just take a look at some of the structure that isn't the active chiral moiety that's driving the kind of chiral selective binding. So this sort of structure here, or this sort of structure here, is meant to illustrate, so the squiggly line would be like the surface of a silica particle. That oxygen would belong to one of those silanols that we talked about before when we were talking about adsorption chromatography. And then this structure here would be some type of silane. And we're going to talk a little bit more about the chemistry that makes this silane click, basically, onto these silica surfaces, onto these silanols, when we get to partition chromatography. But for now, the take-home message is you have this silicon terminated structure. It's got this kind of carbon chain that acts as a tether, as this thing calls it. And at the end of that tether is an R group, and here are the R groups. And these are what are doing that chirally selective binding that we were talking about. So you can see in this structure up here, there's a chiral center right here. It's in the S conformation. Here's a different chiral functionality that would be incorporated into one of these stationary phases. In fact, it has two chiral centers, and it can be used to direct binding of different species. But the point here, the take-home message, is you're seeing some of that binding functionality that we were talking about, right? So here's like a conjugated ring system, so you get a lot of pi stacking type interactions that are going to bind selectively, and it's centered around this chiral center. You're going to get some nice hydrogen bonding opportunities with these carbonyls and that amine. And so the general idea is you look for a lot of functionality that's going to drive intermolecular interactions. It's all situated around some kind of chiral center. So you can get a better look at these things if we look at this is a catalog from Regis Technologies. Here's the web address if you guys want to take a look at this catalog specifically. And obviously it's a sales product, right? So they're going to be pitching their products pretty hard, but there are a couple of nice take-home points here. So let's take a look at these. So here's, first of all, here's why we call them Perkle phases, right? So in 1980, Regis partnered with this guy, William Perkle, who was in Illinois, and he essentially invented this concept. So Regis were the licensees of this thing that William Perkle invented. And they're talking about these advantages of using Perkle phases for separation of enantiomers. And so the context of this is going to be a little bit hard. It'll become a little clearer in a few minutes when we talk about the other methods for doing this. But in general, here are what they're selling these Perkle phases on, right? So the first is this idea of an enantiomeric separation. I don't know that that's a sales pitch. That's just like the purpose of doing it, right? That's not something special that it does. That's just what it does. But probably two things that are going to make a lot more sense as we talk about this further: the idea of column durability and universal solvent compatibility. So that comes from the fact that what we're going to see in a minute are some far less robust chemistries for making chiral selection on a column that would not stand up to really strong solvents or really high pressures quite as well as let's come back here, quite as well as these covalently bound surface chemistries would. Okay, and then I thought this is a really neat idea. It's the idea to the ability rather to invert elution order. So let's scroll down and see what they have to say about that. Ability to invert elution order, and basically it comes from the idea of if you have a structure that, you know, a chiral structure immobilized on the stationary phase particle that's doing a really good job of binding one of your enantiomers, then you know you have the intermolecular forces down. You've got the right kind of configuration of forces to bind to your analyte of interest. So if you just swap the R structure of that stationary phase for the S structure of that stationary phase, you're still going to have the right intermolecular forces to bind your enantiomer. It's just going to bind the other enantiomer, right? If the first, if the R stationary phase did a really good job of binding the R half of the enantiomeric pair, then you switch to the S stationary phase, you're going to get better binding of the S enantiomer. And that's a neat trick. It's going to, I think this thing here even says that it's a desirable feature for enantiomeric purity determinations, right? Because if you can just take these two peaks in your chromatogram and just watch them flip back and forth between two different columns of the same structure, but the different handedness of those chiral centers, you're going to learn a lot about which peaks you're working on, basically. Which peaks are your specific enantiomers, and you'll be able to look at their ratios a lot more effectively that way. Okay, so this is the concept of the Perkle phase, and if you want to learn a lot more about these, I hate to point you towards commercial sources of information because they're always trying to sell something to you, but this is a pretty good one. There's quite a good discussion here just on the basis of these Perkle stationary phases.
So just to summarize on these Perkle type phases, we're looking for basically lots of binding functionality. That is, opportunities for pi stacking. So by binding, we mean non-covalent intermolecular forces, right? Things like hydrogen bonding functionalities, dipole type functionalities that are going to kind of induce those kinds of interactions with your analyte. And we're looking for all of these to surround a chiral center. Okay, and when they do, you're going to get preferential interaction of one half of an enantiomeric pair over the other, and that's just going to be because of the orientation for which these intermolecular interactions will happen more favorably for one half of that enantiomeric pair than the other. So I said we had kind of 2 or 3 ways of doing this. Let's look at another way of doing this that's not based on these Perkel functionalities, and that would be to have chirally selective cavities, basically designing pores, I guess, at the molecular level into the particles where there is um, some kind of chiral center as part of the structure of that pore. And again, the same concept being that one half of an enantiomeric pair will more preferentially have intermolecular interactions with that cavity than the other would, because of the arrangement of intermolecular forces. And so the big tool here, and it's one that's going to come back when we talk about the other way of doing this, that's not chiral stationary phases, are cyclodextrins. So the idea would be to design stationary phase particles where you have these binding pockets, and these binding pockets are basically made of cyclodextrins. So what we'll do is we'll switch over to a screen capture here real quick, and we will take a look at what the structure of these cyclodextrins looks like.
Okay, so here we are back at everybody's favorite source of information, Wikipedia, on the general page for cyclodextrins. If you read this, what you're going to see is that cyclodextrins are kind of a generic class of molecules. It refers to these cyclized glucose rings. And in fact, if you read this, you'll see there's mention that these rings can get really big, 30 to 150 membered rings. The ones that we generally tend to think about are alpha, beta, and gamma cyclodextrin, which correspond to 6, 7, and 8 glucose molecules specifically in this ring. But the point is that those glucose molecules have a handedness to them, right? They are D-glucose as they're represented here. And so if we look closer here, these CH2OHs, they're coming out of the plane at us because this is D-glucose. But if this was L-glucose, they would be going into the plane, which means that they can selectively interact with enantiomers, basically. That handedness will preferentially interact with one handed molecule over the other, one half of the enantiomeric pair over the other. When we talked about these as being chirally selective cavities, this is what we were talking about. So this structure right here kind of shows what they're calling the toroid structure, the 3D toroid shape, roughly. It's like a cone, truncated cone shape. These things take on in their three-dimensional structure. And so those chirally selective cavities we were talking about are basically the kind of the volume inside of these OHs. Again, look at all these OHs, tons and tons and tons of hydrogen bonding opportunities here, right? And that's kind of the central theme for some of these chirally selective stationary phases. So again, we're looking at tons of intermolecular forces, in this case in the form of hydrogen bonding or dipole interactions with these OHs, in an environment that is itself chiral by nature of being made up of D versus L glucose. So that's the concept of cyclodextrins as chiral selectors. Right now we're talking about them in stationary phases. In a minute we're going to talk about them in mobile phases.
So a couple things we can say about chiral separations, especially with regards to these chirally selective cyclodextrins as stationary phases, or a stationary phase functionality. I guess the first one would be to say that I'm going to say often, but not always. We see retention factors for, so suppose we were looking to separate these structural isomers of para versus ortho versus meta. Very often what we're going to see are higher retention factors for para versus ortho versus meta. Now this isn't a hard and fast rule. This is why we're saying often. And actually that's kind of the theme that we haven't really gotten to yet in these chiral separations, is that they're really hard. They're really hard methods to develop if you want to try and make chiral separations work. And so you get these little rules of thumb like this, but really it's going to be a lot of method development to figure out exactly how things are going to bind and when things are going to bind and what's the right stationary phase. Here's something else we can talk about. Why would you use, say, alpha cyclodextrin versus beta cyclodextrin versus a gamma cyclodextrin? Let's look at these, that CD toroidal structure that we were just looking at. So it looks like that. So we're just basically going to show the space that these things fill. So you can imagine basically this cone or funnel shape, the walls being lined with those D-glucose that are cyclizing, and they have a kind of a big open end where things are going to be able to bind in, and a smaller end where this thing's going to be tethered to a stationary phase particle. And if we look at, so we can consider basically the size or the shape of this cavity as one driving factor why we would use alpha over beta. So we have two different diameters here, right? So if we look at alpha cyclodextrin, we're gonna basically the minor diameter, we'll call that, is gonna be on the order of half a nanometer, and it will open up to the larger diameter on the order of 1.4, 1.37 nanometers. So that defines kind of the geometry of this binding cavity. If we look at the beta cyclodextrin, it's a little different. So 8 nanometers to 1.5 or so. And finally, if we look at the gamma, which was the largest, this is this is 6, 7, and 8 glucose subunits in that cyclodextrin ring. And at this point, the minor diameter is almost a full nanometer, and this will go up to almost 1.7 nanometers. And so one of the driving factors that would cause you to look at a stationary phase produced, say, by gamma instead of alpha cyclodextrin is how big of a molecule are you looking to chirally select, right, in that cavity. And these geometries help you do that. Okay, so finally, we said there's I said 2 sort of 3 ways to do it, and that's because way number 3 to do a chiral stationary phase is really, really similar to this, and that is to use naturally occurring polymers. Well, guess what? These polysaccharides that we've just been talking about, these are naturally occurring polymers, right? The idea is that there are other naturally occurring polymers. For example, proteins are a good one. Often we'll see chiral stationary phases made of just these highly abundant proteins that are cheap. So something like albumin. This is a protein that comes from, well, all sorts of biological sources. Actually, it's in your blood. It comes from eggs. It's all over the place. A lot of the time when you're eating a protein-rich meal, it's because you're eating a ton of albumin. But the idea is nature, it's kind of one of these mysteries of nature, but biology has naturally selected a preference of one-handed amino acids over the other. And so if you have a protein, which is just a big polymer string of amino acids, you have a ton of chiral functionality in there. And so, you know, forcing things to specifically or non-specifically interact with albumin is going to have some chiral selectivity to it. Another good example here would be cellulose, which is very similar to the concept of the cyclodextrins. The difference just being you can get these much larger, more extended structures than just the several unit cyclized cyclodextrin structures. Okay, so these are the concepts for chirally selective stationary phases. The concept, the second way, the second approach to doing this would be a chirally selective shocker mobile phase, right? If we can do it in the stationary phase, we can do it in the mobile phase. The idea of making the mobile phase an environment that selects, that preferentially binds or prefers one of an enantiomeric pair. And this is done pretty much exclusively one way, and that is by adding selective binding agents or reagents. Adding something to the mobile phase that will prefer binding to one of your one of an enantiomeric pair over the other, and therefore it's going to push on extraction equilibrium, right? It's going to basically use up part of, you know, half, so preferentially one half of a pair of enantiomers, and so the equilibrium will be able to push more of those into the mobile phase. So this can be done with specific binding partners. This is the idea that you have a pair of isomers and you have something that binds one better than the other. You use that something that binds one better than the other as an additive for your mobile phase. And therefore, your mobile phase will now more selectively, dissolve your the one that is being bound to a partner. The downside here is that it can be hard, if you're trying to do this preparatively, it can be hard to purify at the end, right? So if your chosen isomer is bound to some kind of partner the whole time it's going through the column, and that's why it doesn't get extracted onto the stationary phase, well, in that case, it's coming out bound to that binding partner, right? So you're going to have some strategy to remove it, and presumably it bound pretty strongly if it survived this strong extraction environment inside of a chromatography column. And then something we've already seen, which is cyclodextrins used as additives, as mobile phase additives. And the idea here is it's not going to be as specific or selective as a binding partner. It's going to be based on some of these just generic intermolecular interactions that we talked about when it was a stationary phase. Basically, then all we're doing is cutting that tether and having a bunch of it in the mobile phase to do the same thing, right? To have this selective binding of one isomer over another. So there is one final take-home message, and it kind of goes with all of this chiral separation stuff, and I kind of gave it away a moment ago, which is this. So the take-home on chiral separations they're really hard. We don't have a lot of high strict rules for how these things, how these separations work. There's not a really strong body of theory that will allow you to predict ahead of time if something's going to work. And so this means a lot of trial and error. So a lot of trial and error, and quite a bit of, well, we'll say art more than science at the moment. Hopefully, there's a lot of folks that will make that less true as time goes on. But the bottom line is it takes lots of time to develop a chiral separation method, and therefore it takes lots of moolah to make that work. This is actually a huge part of separation science in the design of novel drugs and novel materials. So, guys, I think this is where we're going to stop on chiral separations. When we come back next time, we are going to talk about partition chromatography, which is the basis of all of the original extraction-based chromatography theory that we talked about for most of the semester, right? What we're going to do is we're going to see some of the practical aspects of building stationary phases that make this happen. And it's going to kind of lead us into some of the far more common, the most common modes of doing HPLC and liquid chromatography in general. All right, guys, stay safe out there. Stay healthy. Wash your hands. Don't lick any doorknobs. And I will see you, or speak to you at least again real soon. All right, take care.